Now, the very first question that we should ask is that how do we get X-rays? So, so the most simplistic answer to this is that we get it by very large quantum jumps. Now you guys know that quantum jumps are like, within a gas or something, or a material, they're like discrete energy levels that we already know now, thanks to Neil Bohr atomic model, that if there is a very big quantum jump, we might end up getting X-ray, okay, or X-ray photon. So we should understand that in a hydrogen atom, even the largest quantum jump gives us UV light, and in terms of energy, photon, UV has less energy compared to X-ray, so we need some other material. So hydrogen cannot be or cannot give X-rays, as simple as that. So to do that, elements like tungsten or above, which are like higher, in the atomic number, gives us X-rays. So we excite an electron to a very high state. Okay, so we need to make sure that it jumps like up the energy level at a very high energy level, so when it comes down it can give us that. Now in order to do so, we use a very wasteful technique, and that is basically the direct bombardment of beta or beta radiations, whatever you call it. All right. Interesting.
Sir?
Yes. Yes.
Why is it wasteful?
Yeah, I'm gonna just tell you this in a bit, okay? Just in a bit. Don't worry about it. I have all your answers to all your questions. Okay. So I just want to tell you this is wasteful because this process, like direct bombardment, is only 2% efficient. and rest 98% is dissipated as heat. Do you understand, Abdul Moise?
Yes, sir.
And this is like even in 2%, right? Varies like that because we strike electrons with hopes that they will make the right quantum jump, because if they don't, they can release other things like they can jump like step by step, so they can release other waves and not x-rays at all. So that's a big deal, all right, for us. Gotta remember that. So I'm gonna show you the structure of it. You can take a picture of that because it takes a lot of time to draw that, and you won't be required to draw anything like that. So yeah, lucky you. I'm just showing you so that you guys can actually see that how it functions, and then we can write about it. Okay, so it looks like this. Okay, so once upon a time I drew it with hand. Now you don't have to. So I'll just explain it to you. So if you see, there is an electron gun at a very high voltage, like 10,000 is given to it. There's an evacuated chamber, and the electrons are released through thermionic emission, which means like the coil is heated up, the electrons are released. They are turned into stream or a beam of electrons by using cathode and anode, like you can see right now. Just hold on a second, please. Hello. वालेकुम सलाम जी 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 Inashuja 157P Wilberg 3 or no owned it. Okay. Now, so they basically strike on this tungsten metal that you see, okay? And this metal basically is constantly rotated. The reason why it is rotated is that if the electrons keep on striking just one part of it, it is going to, the heat is so much that it's going to basically melt the metal. So what you do is you keep on rotating it, you transfer the heat towards the heat sink where a water jet basically cools it down. The other thing is that this rotating disc is basically angled at 45 degrees. So when it strikes, because it follows the laws of reflection, so a strike of 45 degree would also release the photons at 45 degrees downwards like this. Then there are certain aluminum filters. I'll tell you what is the use of it later. And then there are like shutters like this, just to control the sharpness of the image. And then there's a lead grid and x-rays are released, which passes through the patient. So this is the complete diagram or the design or assembly of the inside of an x-ray machine. Is it clear, everyone? So you can just
sir,
yes.
Where do the other waves go?
Which other waves? Like
So if
UV.
it's not on the right quantum level, you said that other
Yeah.
waves are gonna release as well.
Yeah,
So where do they go?
they're just released in the environment. Some of them are absorbed by the lead. Some of them are filtered by aluminum, like that. All right.
So we're not getting like exposed to any other waves in a
No,
hospital,
no,
for example.
no, no. Getting exposed to X-rays enough. That's worst. Okay.
Yeah.
So other waves like UV or other radiations, it doesn't really matter. The only bad rays, like in good amount of quantities, would be X-rays and gamma, and that's not good. Okay, so we don't want to get exposed to that. But yeah, it's like that. The others are absorbed, so don't worry about that. Even some of the X-rays are absorbed, so that's how it works. Okay, now can I move on now? So this is the what we're doing is we're doing the production of X-rays actually right now. So now let's go to an evacuated chamber is created at low pressure. Thermionic means that we're heating. When we heat and electrons are emitted, that process is called thermionic emission. Occurs in the electron gun region. All right, like that. And a beam is targeted onto the rotating anode disk, like that. The disk rotates at 45 degrees continuously, so that it is exposed at different areas, like that. And then rotating anode is continuously cooled so that it does not burn, since this process releases a ton of heat. Copper rod transfers heat to the heat sink, where it is cooled through a water jet, like that. Then the electrons absorb energy and go to high quantum levels. They then jump down to give X-ray photons. Now, it is a very inefficient, like I said, process, since most of downward jumps are ultraviolet and infrared, and like I said, 90% of heat is dissipated. But what can we do? We still need it. All right. Now the last thing you should remember in production of X-rays, this is an important note. And that is the accelerating anode, cathode voltage is around 10 kilovolts to 100 kilovolts. That's how much we need. Okay. And the other thing is, we rotate the anode to prevent it from melting, and for more exposure to electrons. We want more areas of the district article. That's why. Right? So you can write it down. If you have any question, you ask me, okay? I'm just gonna get some water, and then when I'm back, we can discuss it even further. Okay. All right. Aman, Suman, and Gatika, and Nadia, and Abdul Mois. Do you guys have any questions now?
Sir, what is accelerating anode cathode voltage?
Okay. Everybody's written it, then I'll answer it. Okay, if you look at it, this is the electron gun, right? The electrons are released, they need to be, they're given, work is done by the electric field. That's cathode basically pushes them towards this, anode also, attracts them. So that's why they're accelerated, right? Okay, got to go. It's the same thing like we did, you remember, in, what was that? Magnetism.
Yes.
Yeah, same thing, same way. We need electron. We have a lot of use of electrons. Thank God we have them. Okay, I'll be back getting some water and then we'll continue. All right. Yes. You guys were saying something? Okay. Should we go forward then? So, yeah. So we're gonna go to the next one. The next sheet, basically. Now we're going to start with the post X-ray production. So when the X-rays are produced from the tungsten metal, now there are a couple of factors that we need to see. Okay, so one by one we're going to look at those factors. The first factor that we're going to talk about. Okay, I want you guys to number this, and if I lose track of the numbers, you guys need to remind me. Okay, what number we are on. So first number would be hardness and softness. Okay, so this is our first factor. So hardness, softness refers to wavelength, which is lambda, of X-rays. Now you need to remember the X-rays are not like one wavelength, there are range in that. So there are a couple of wavelengths of X-rays that come up. So hard X-rays penetrate the body and pass through it. And hard X-rays always will have high frequency and low wavelengths compared to other X-rays. Okay, and the soft X-rays are absorbed by the body. And you guys need to remember, soft X-rays have low frequency compared to others and high lambda. Alright, like that. Okay. Then comes exposure. Exposure, like the word suggests, right, would be a measure of total time X-rays are incident to the body. So it depends on time, and I'm gonna write something here in a star, just this is an important note, that longer the body, like it doesn't come in the definition, but it's an important thing that you need to remember. Longer the body, I need to write the body is exposed to X-rays, then it would cause greater dosage and intensity. And we need to remember. Okay, now we're going to talk about intensity and dosage, don't worry about that. So the thing is, then comes intensity. So intensity is like the brightness of X-rays. So this is the simplest definition, and now write the note. Brightness is increased by increasing the tube current. Basically, it means how many electrons are, ejected from that thermionic emission. That's fine. Okay, then you have dosage and Dosage is basically defined as the measure of total X-rays absorbed by the body. It occurs according to the nature of X-rays and nature of bodies. Nature of body means that what kind of, like it's a bone or, tissue or fat or whatever. Now, put a star here and write that high density bones absorb more X-rays and soft X-rays are easily absorbed. So in tissues and stuff, it's X-rays pass through generally. You remember that. All right. I hope everything is clear. Okay, cool. Now, the fifth thing we're going to write is sharpness. Okay, so we're going to write these two things first, and then in tomorrow's class we need to do something out, because these are the most important things that we're going to write now. So sharpness refers to the ease with which the edges of structure can be determined. Okay. Now put a star and write that it implies that a sharp image has a clear and defined edges. I'm going to tell you what basically that means, okay? So first then we're going to talk about contrast. And contrast basically is the degree to which organs can be separated or identified from each other. So we're going to stop till here, and then we're going to work later. I just want to explain these two things, which is very important to learn. By the way, do not make fun of me because I've never studied bio in my life. So I believe a bone looks like this, okay? And I believe that a heart looks like this. Is that clear, everyone? Okay, so imagine this is the heart, this is the bone. So right now, if you look at this image is a pretty sharp image. Why is it sharp? Because we have defined edges and we can see those. Like, we can see that, okay, this is like a particular thing, and that's a particular thing, or there's a change here like edges. But if the same thing was like this, so that would mean that now this image is not sharp anymore because we do not have defined edges. Is that clear, everyone? Good. Now, contrast means that suppose if this one, okay, suppose we have a pink heart like this. X-ray doesn't show you pink, but it shows you black and white, right? But it's fine. I'm just giving you an example. So if there's a pink heart like this and there's a yellow bone like this, so right now we can see that both have, like, you can separate them, like you can see color difference. Usually it's darker or whiter, but it's color difference we can see. But what if they were like this? And the yellow was like this. Now, as you can see, you might still be able to see them, but the color is so uniform, or it's kind of uniform, that there's no contrast. So contrast basically is how color defines two different organs or things, whereas the edges are defined by how sharp the image is. Is it clear, everyone? Okay. So I'm gonna see you people in the next class then. We have a lot to do in this chapter. This is a long one. So then we'll discuss and finish it off. I think we'll finish medical, no, at least some of it. All right.